Projectile motion is motion in two dimensions. There is a vertical and a horizontal velocity component. So if we look down here, we can see this might be a little ball here rolling off along a table and then off the edge, and it follows this kind of a path. So the velocity of the ball has an x component, which is the horizontal, and a y component, which is the vertical. Now, two important things about this is that the x component here is constant. And, of course, we are neglecting air friction there. The y component here is acting on gravity, and it acts exactly like the free fall motion that we studied in the previous chapter. The other thing is that these x and y components of the velocity are totally independent of one another. So the time that it takes this object to fall freely is the same regardless of whether it has this x component here or not. So a very interesting little experiment that you can do is if you can shoot something horizontally off a table like this and then drop it simultaneously like this, both objects will hit the ground at the same time. So here is a little problem we can solve with projectile motion. The stunt driver, Evel Knievel, drives a motorcycle off a 50-meter high cliff and lands on the ground 155 meters from the base of the cliff. We want to determine his takeoff horizontal velocity. Okay, now since those x and y components are independent of one another, from the height of the cliff, we can calculate what his time in the air is, because it would be the same as the free fall time. And we can use the formula y equals v0 yt plus 1 half gt squared. Now, the initial component in the y direction, right, that's the vertical component, that's 0. He's got a horizontal component, but the initial velocity in the y direction is 0. So we have y is just equal to 1 half gt squared. We solve for t, which is the square root of 2y over g, and we compute t to be 3.19 seconds. Okay, so now, if he's traveled that 155 meters from the base of the cliff in 3.19 seconds, that x velocity, horizontal velocity, which is constant, is just going to be equal to displacement divided by time. So it's 155 meters divided by this time, 3.19 seconds, and the velocity comes out to be 48.6 meters per second. So this is a different kind of problem that you'll often see. We've got a football that's punted from the ground with a velocity of 35 meters per second and an angle of 30 degrees. We want to determine three things: the maximum height, the time in the air, and the horizontal displacement. So this little diagram here, this dot would represent football. We've got the velocity here with which it's kicked, 35 meters per second, and this angle relative to the ground here is 30 degrees. Okay, now the first thing in these problems, you always have to compute Vx and Vy. So we use the trigonometry that we saw earlier in this chapter to find the x component, which is going to be this way. We're going to use the cosine function. So cosine of 30 is equal to Vx over 35. Vx is 30.3. And then Vy, which is this direction, that'll be the sine function. So sine of 30 is equal to Vy over 35. Vy is 17.5 meters per second. Okay, now we go on to the various parts of the problem. First thing, maximum height. So to find the maximum height, we can use this formula here, which you've seen before, recalling that the final velocity of the object at the maximum height is going to be 0. Right? So that's the velocity in the y direction is going to be 0. So we solve for y, and so we have y is equal to vf squared minus v0y squared over 2g. So there it is, that final velocity is 0. Now, this initial velocity, very important here, that's going to be that vy, the y component, not the 35, but vy here. Okay, so that's going to be 17.5. That's got to be squared, divided by 2, times a minus 9.8 meters per second squared. We solve for y. Y is 15.6 meters. So the maximum height, this height right here, that the football travels, is 15.6 meters. So the next part is to find the time in the air. Okay, so we've done this kind of a thing before. We're going to use this formula right here, and we're going to set y is equal to 0. Again, the reason why we do that is because the net displacement in the y direction is 0. The ball ends up at the same point vertically, from where it was kicked. So therefore this is 0. So we have 0 is equal to, again, this is the initial velocity in the y direction, the y component, 17.5 t plus 1/2 times 9.8 times t squared. And we did this before. The way to solve this is simply to factor out the t. Okay, so we get that. And as I explained before, when you multiply two things together and you get 0, then one or the other must be 0. So two solutions. One is t is equal to 0, and then the other solution is when this whole term here, 17.5 minus 4.9t, is equal to 0. So we set that equal to 0. We solve for t, which is 17.5 divided by 4.9 meters per second squared, and we end up with 3.57 seconds. Once again, both of these solutions are valid. This is the one that we're after, though. This is the time that it takes that the football is in the air. Okay, so now we know that. Now, to find that horizontal displacement is easy, because we can use that x component of the velocity, which is constant. So displacement is equal to vx times t. We now know t, 3.57 seconds. So we use now the x component of the velocity, which we computed to be 30.3 meters per second. We multiply that by this time in the air, 3.57 seconds, and we get 108 meters as that horizontal displacement. Now the last thing is this range equation. The range equation is used strictly for computing a horizontal displacement for the projectile. For example, in this previous problem that we did, you could have used this formula to calculate what the range of the projectile was, and you'd get the same answer as we got in that previous slide. Okay, now one thing about this formula now, this initial velocity here is not a component. This is just whatever the initial velocity was of the projectile. Notice this is sine of 2 theta divided by g. I believe this is derived in your book. Okay, so here's an example. We want to find the angle that a projectile needs to be fired at if it's got an initial velocity of 40 meters per second and you want to hit a target 100 meters away. Okay, so we're going to use this and we're going to solve for ultimately the angle. So we have to start out by solving for the sine of 2 theta. So the sine of 2 theta is going to be equal to the range, which in this case we know is 100 meters, times g, 9.8, divided by the initial velocity, remember in this case not a component, 40 meters per second, and we have to square that. We end up with this value, 0.613. Okay, now we do an inverse sine of 0.613, and that's going to give us 37.8. So that tells us now that 2 theta is 37.8 degrees. So now to find theta, we simply divide 37.8 by 2, we get 18.9 degrees. All right, now, however, that's not the whole story, because if you were to, on your calculator, punch in the sine of 142 degrees, you would get that same value, 0.613. So, another solution to this is take the 142 degrees, that could also be 2 theta, divide that by 2, and you get 71 degrees. And either one of these angles would work. So in other words, if the projectile cannon, whatever it happened to be, was fired at this angle, at this initial velocity, it would hit the target, or if it was fired at this angle, with this initial velocity, it would hit the target. Now, just one more point. The second value here, this 142 degrees, where that comes from, is that's always going to be 180 degrees minus this 37.8. So 180 minus the 37.8, that's where I got the 142 degrees, and then divide that by 2 to get that second angle. All right, now one last thing. You look at that range equation right here. What angle is always going to give you the maximum displacement? I'll give you a second here. You can pause the video if you want. Okay, well, the angle that will always give you the maximum displacement is 45 degrees, because sine of 2 theta. Now, when you take the sine of any angle, the biggest number you're ever going to get is 1. And that's when the angle is 90 degrees. So, if theta is 45 degrees, you multiply that by 2, sine of 90 is equal to 1, and so the range is going to be equal to the 0 squared divided by g. That'll always give you the biggest range, 45 degrees. If you go less than 45 degrees, you'll get less of a range, and greater than 45 degrees, you'll get less of a range.